Let's jump right into it. Today, we are stepping into what is honestly a pretty fascinating detective story. We're looking at how modern machine learning and natural language processing can basically act as a compass, guiding us through the incredibly complex and, let's be real, often chaotic world of research mathematics. It's this awesome journey from raw, unstructured data to intelligent prediction, and I am so pumped to walk you through this explainer today.
So, right off the bat, we have to ask the big question. How exactly does AI make sense of human math? And just to clarify, we're not talking about your high school algebra or basic calculus here. No, we're talking about dense, highly abstract research-level problems that are literally pushing the boundaries of human knowledge. Trying to organize and actually understand this level of math, yeah, it's an immense challenge.
And the sheer scale of that challenge really hits you when you see this number, 14,000. We are diving into the Amphora/Research Math 14K dataset. This thing is a massive collection of roughly 14,000 complex math problems, and they were mined straight out of arXiv, which is, the absolute premier repository for scientific papers.
All right, here's our roadmap for today. 1. The Research Math Challenge. 2. Prepping the math data. 3. Mapping the landscape. 4. Building semantic search. And finally, 5. Predicting the unsolved. Let's get into it.
Section 1. The Research Math Challenge.
Okay, so before we start building any flashy AI tools, we really need to understand the core problem. arXiv is absolutely brilliant, but it is also an overwhelming mountain of complex math. Just put yourself in the shoes of a mathematician for a second. Trying to find the signal in the noise of thousands of academic papers, it's like finding a needle in a haystack. You need to figure out what specific jargon means, how different super niche fields connect, and most importantly, what problems are actually still unsolved. Doing all of that manually, it's a monumental human task. We desperately need a way to automate how we understand this text.
Moving on to Section 2, Prepping the Math Data.
Now, you can't just dump a bunch of raw academic papers into an AI and expect magic. You've got to clean up your workspace first. First, we load the dataset into a pandas data frame just to see what we're working with. Then, we filter it to keep only the problems of a meaningful length. Why? Because we need to make sure the AI actually has substantive text to chew on, while cutting out all the useless noise. And finally, we analyze how this data is distributed.
And when you visualize that distribution of open status categories across all these different mathematical fields, it's pretty amazing. You get this instant bird's-eye view. You can literally see exactly where the solved, unsolved, and partial problems live across different domains. It immediately brings structure to what used to just be a chaotic mountain of text. It's a real game changer.
Which brings us to Section 3, Mapping the Mathematical Landscape. So, to build our map, we first need to establish our landmarks. To do this, we use a classic technique called TF-IDF. The best way to think about this is like a giant AI highlighter. It quickly scans through the problems, which are naturally grouped by their top-level mathematical field, and it scores the words. It's basically looking for the absolute most important defining phrases within that massive body of text.
By pulling out these strong keywords, the AI is doing researchers a massive favor. It helps them instantly understand the foundational topics and the terminology that dominate different areas of math. I mean, think about it. You don't need to sit down and read 14,000 papers to figure out what a specific subfield is focused on. This TF-IDF extraction just hands you the most critical vocabulary right off the bat.
But, as you know, a bunch of vocabulary words isn't enough to draw a real map, right? We need actual coordinates, and that is where sentence transformer embeddings come into play. What we do is take each math problem and convert it into a semantic embedding. You can picture these as GPS coordinates assigned directly to the text. The AI then places problems with similar mathematical concepts physically closer together in this mathematical space. It essentially gives the system a true semantic understanding of the entire landscape.
There's a catch, though. These AI embeddings, they exist in hundreds of dimensions, which, frankly, is impossible for the human brain to visualize. So we bring in tools like UMAP or PCA to literally squish those multidimensional coordinates down into a flat 2D visual landscape. And once we've reduced it, we can actually look at a beautiful visual plot of the problem landscape perfectly color-coded by field.
Of course, the real test here is figuring out if the AI's map actually makes sense to a human mathematician. To check this, we apply k-means clustering. This lets the AI group the problems naturally on its own. Then, we compare how the AI clustered the math fields against the human-labeled taxonomy that was already built into arXiv. And the results?
By using standard statistical metrics like ARI and NMI, we can scientifically prove that the AI's semantic understanding aligns remarkably well with how actual human mathematicians organize these fields. It's spot on.
All right, moving into section 4, building semantic search.
Because let's face it, a map is pretty useless if you can't navigate it. So, using those GPS coordinates, the embeddings we were just talking about, we build a semantic search function. This lets a researcher type in a query and boom, they instantly retrieve the most similar research problems. By computing similarity across all those embedded problems, the tool easily sniffs out near duplicates and pulls up strongly related problem statements. It completely transforms a chaotic database into a highly precise searchable engine.
Finally, section 5, predicting the unsolved.
Guys, this is really the climax of this whole data workflow. Because our embeddings capture the deep, underlying semantic meaning of the text, we can actually do way more than just search. We can predict. We can literally train a classifier directly on these embeddings to predict the open status label of a problem. The AI learns the super subtle linguistic and contextual patterns that separate a fully solved theorem from a problem that is still a complete unsolved mystery to the mathematical community. How cool is that?
As our source material perfectly puts it, embeddings can support both exploratory analysis and supervised prediction tasks. We started with a data set of 14,000 intensely complex math problems, and by using modern NLP tools, things like TF-IDF, dimensionality reduction, clustering, and classification, we completely demystified its structure. We organized the whole shebang. So, we've basically built a practical way to study, retrieve, and even predict the status of the world's hardest math, which leaves us with a really exciting question to chew on. If machine learning can bring this level of clarity and predictive power to complex research-level mathematics, what unsolved mystery is AI going to map next in the landscape of scientific discovery? Thank you so much for exploring this with me today. Keep learning and keep questioning.